Open Task Manager. If your computer is equipped with a modern CPU, you will very likely see information like this. 8 cores, 16 threads. At this point, many people have a question. Wait, when I bought it, it was clearly an 8-core CPU. Why does the computer tell me there are 16 threads? What are these extra 8? Is the CPU secretly working overtime on its own? Or does 16 threads equal 16 cores? In fact, behind this question lies the most important design philosophy of modern CPUs, and understanding it will not only let you know what threads are, but also why even a CPU with billions of transistors often still spaces out. Let's start with the core. Many articles like to compare a CPU core to a worker in a factory. Although this analogy is not wrong, it hides one fact. A core is not an abstract concept. It is real hardware. If you cut open a CPU and look under a microscope, you will find that each core has its own arithmetic logic units, registers, caches, and pipeline structure. Simply put, one core is a complete computing system. It can execute programs independently. Suppose your computer has 4 cores. You open a browser, a music player, a document editor, and a game at the same time. The operating system can assign these different tasks to different cores. This way, multiple programs can run simultaneously. This is true parallel computing. 4 cores means 4 sets of independent hardware. Theoretically, they can execute 4 different tasks at the same time. That sounds perfect already. So here's the question. Since a core can already execute programs independently, why was the concept of threads invented later? The answer is because CPUs are far less busy than you think. Many people see CPU usage at 100% and think the CPU is doing crazy calculations all the time. In fact, that is not the case. The biggest problem for CPUs has never been calculating too slowly, but waiting too long. For example, a program needs to read a piece of data. This data might not be in the registers, nor in the L1 cache, nor even in the L2 or L3 caches. Eventually, it has to go to main memory. Modern CPUs run extremely fast. A 4 GHz CPU can execute about 4 billion clock cycles per second. In contrast, memory is much slower. Reading data from memory once might take hundreds of clock cycles, sometimes even more. What does that mean? It means after the CPU issues a read request, it does nothing for a long time afterwards. It can't do anything. There is a very interesting fact. Modern CPUs have a lot of computing resources inside. For example, integer arithmetic units, floating point units, load store units, vector units, pipelines, execution ports, and so on. These hardware components are very expensive. They take up a huge number of transistors. But when the program is waiting for memory, these hardware components may all be idle. It's like a factory with thousands of employees. Suddenly, because raw materials haven't arrived, all workers can only sit there idle. For CPU designers, this is a huge waste. So they started thinking about a question. If one program is waiting for data, could we let another program come in and work during that time? If this can be done, would CPU utilization increase? Thus, thread technology was born. More precisely, modern processors use a technology called Simultaneous Multithreading, abbreviated as SMT. Intel calls it hyperthreading, AMD simply calls it SMT. Different names, but the principle is basically the same. To understand how SMT works, let's first see what's inside an ordinary core. A core has arithmetic units, caches, pipelines, execution ports. These are the truly expensive parts. If you wanted to turn one core into 2 full cores, the cost would be very high. The chip area would almost double. Power consumption would also increase dramatically. So engineers chose a smarter approach. They did not duplicate the entire core. They only duplicated a portion, specifically. They duplicated a second set of registers, a second program counter, a second thread context. These things take up very little area. This way, the same core can maintain 2 threads simultaneously. From the operating system's perspective, it looks like it has become 2 logical processors. For example, physical core 1 becomes logical core 1 and logical core 2. Physical core 2 becomes logical core 3 and logical core 4. Thus, an 8-core CPU reports to the operating system, I have 16 logical processors. That is what we see in Task Manager. 8 cores, 16 threads. But there is a particularly important misunderstanding here. 16 threads does not equal 16 cores. Many people, when first seeing CPU specifications, think, does 8 cores, 16 threads mean having the performance of 16 cores? The answer is no. Because the 2 threads actually share most of the hardware in a single core. They share caches, share arithmetic units, share execution ports, share pipelines. These resources have not increased. They are just used together by 2 threads. Therefore, when one thread is waiting for memory, another thread can continue executing using idle resources. This improves utilization. But it does not magically create new computing power. So, 8 cores, 16 threads is usually faster than 8 cores, 8 threads, but it is obviously slower than a true 16-core processor. So how much performance improvement does SMT bring? The answer depends on the workload. If the program frequently waits for data, then the benefit is obvious. For example, video encoding, 3D rendering, scientific computing, large-scale software compilation, database processing. These tasks typically generate a lot of memory accesses. The CPU is often in a waiting state. SMT can effectively use these idle cycles. Performance improvement might reach 20% to 40%, sometimes even more. But if the program already fully occupies the core resources, the situation is different. For example, some games or tasks that highly depend on single-thread performance, the two threads will compete for the same set of execution resources. In this case, the benefit of SMT may be limited, sometimes close to zero. Therefore, more threads is not always better. The key lies in whether the program can effectively use these extra execution opportunities. There is another side effect. The two threads share L1 and L2 caches. One thread may evict data just stored by the other thread, causing lower cache hit rates and actually hurting performance. That's why some professional gamers manually turn off hyper-threading in the BIOS, specifically for running games. Having said this, we can finally answer the original question. Why does an 8-core CPU show 16 threads? Because your CPU did not suddenly gain 8 extra cores. It just learned a smarter thing. When one thread stops because it is waiting for data, it immediately lets another thread take over the work. That way, the expensive computing hardware does not go to waste. So the emergence of threads was not to create more cores, but to reduce waiting time. In fact, if you study computer architecture in depth, you will find an interesting phenomenon. The biggest enemy of modern computers is not computation, it is latency. CPUs get faster and faster, but memory can't keep up. Storage can't keep up even more. Networks are even slower. A huge amount of time is spent waiting, and the essence of thread technology is trying to reuse that waiting time. So next time you see 8 cores, 16 threads, do not interpret it as the computer has 16 brains. A more accurate statement would be your CPU only has 8 real workers. But when one worker is waiting for materials, it immediately hands the tools to another worker to continue working. That is why 0.8 cores end up showing as 16 threads.